Welcome back. This is Dr. Christy Patton-Lukes, and in this lesson, we are talking about separations and separation techniques and sequencing. The slides that I'm using are taken from Turton's textbook for design class. So you'll be seeing a lot of this information again later, but this does in fact go along with what we are doing in our 1CAT textbook. So first, separation isn't necessarily distillation only. And so we're going to have to make decisions about what separation techniques we're going to use. Distillation is by far the most broadly used in so many ways, but it's not the only way. So as you're making decisions, part of what you're going to have to decide is distillation the right technique, or do I want to do other things? And some things I'll be able to do partially with distillation and then need to use some final finishing steps. So these are just simply some guidelines to help make those kinds of decisions. And the first thing is, whatever you do, if you can remove the largest product stream first, you're going to reduce the size of all subsequent pieces of equipment. And that will reduce both your purchase price for the equipment and your operating costs. So that's going to be something that's really significant. When you look at a stream and you're trying to figure out what do I want to do first, get rid of the biggest piece of it. So if you're doing distillation, you're going to also want to look and see which one has the largest heat of vaporization. Because if you remove that one early on, it's going to reduce how much energy you need to put in the reboiler or take out in the condenser. This third little guideline sounds so silly, but when you're doing a sequence of multiple distillation columns or other kinds of techniques, a lot of times people look at it and say, oh wait, I could put this over here with this. If you have separated things, do not put them back together. So always kind of look at your total logic of your flow stream and make sure that you haven't accidentally taken something and recombined it with something that it was originally separated from. In complex systems, it's kind of frequent that students end up doing that. Where you can, do the easy separations. If two chemicals don't want to be together, good, take them apart. That will again reduce sizes and everything else, and that will be an easy step. If you have to deal with raw materials, don't waste your extra raw materials. So you're going to send things back and recycle them, maybe to a reactor. Don't over purify streams. If a customer says they need 99% purity and you're providing them with 99.99% purity, you're wasting a lot of effort to get that extra purity. So try to avoid over purifying. Another little piece of advice is to remove the hazardous chemicals or the corrosive chemicals first. The rationale for this is that makes the rest of the process safer, and it means I can typically use less expensive materials of construction on the rest of those pieces of equipment. So that's going to also be a cost saving. And as you're doing things, if you're like, well, to remove this chemical, I'm going to need some expensive, chromatography or something like that. Do that last when you have the smallest possible quantity to be removed and the smallest possible quantity of material to process. So always do the cheapest early on if you can. Now, if you've settled on distillation as your primary separation technique and you have multiple components, then you're going to have to deal with something where maybe I bring in a mixture and I have A, B, and C, just a very simple little mixture here. And maybe I just purify off A first, but that means that my bottom stream is going to contain those less volatile, B and C. And so I would need a second column that could separate out the B and the C. So if I'm dealing with a situation like this, what kind of order should I do? Because this seems fairly logical, right? One thing that you need to be aware of is that I've listed these so that they are in order of volatility. Okay, so normal boiling point would be a way of evaluating that. And I can do a split, so if I remove A, then A goes to the top, it's the distillate, and B and C go to the bottom's product. I could also have equally well removed C, and A and B would have gone to the distillate, C would have gone to the bottom product. But I can't just like sneak in here and just pull out the B first. Okay, that's not possible. So I'm going to have to remove things in cuts. So I'm going to list my chemicals in volatility, and I'm going to look for where do I want to draw the separation line. We realize that this won't be a perfect separation. There will be a little bit of B and maybe some C in this one, and there will be a little bit of A down here. But my focus is going to be to try and get fairly pure A with very little A in the bottom string. And here, fairly pure B, fairly pure C. This would have a little bit of A, maybe a little bit of C. This probably wouldn't have any A in it, but it might have a little bit of B. Okay, so how do we decide where to make these cuts? And the key really is looking at that relative volatility. And you look at the relative volatility for where the split is. So if I'm doing this one here with A, B, C, then what I'm looking at is the alpha for A and B, and I'm comparing that to the alpha for B and C, two that are in line next to each other. And I look and see those, or it could be the key components, but I'm looking for those, and I'm going to choose one with a large relative volatility. And in particular, if the relative volatility is not greater than 1.05, I'm going to find this to be a very challenging separation to make. Now, once we've made decisions based on that, which is a really key concept, the other thing that we want to think about are how expensive is this going to be to operate? How big is the tower going to end up being? And so these additional points are going to help us narrow that down. So one, the reboiler duty is not excessive. Each of these was a reboiler here that's going to send material back. And that reboiler requires a lot of energy. And if I have energy going into it, that's going to be a cost every day for the entire time this system operates. It may be 50 years. Do you want to make something that's going to use a lot of energy every day for 50 years? Probably not if you had a cheaper option. So this is one that we need to always kind of keep in our mind, is that this is the major expense of operating a distillation column. We also want to keep an eye on our pressures, because the pressure, if we approach the critical temperature by raising or lowering our pressure, then we are going to end up with something where I cannot separate by distillation. I won't be able to get that two-phase split. And I don't want it to be so that I'm so close that on a day where the pump was just over exuberant and increased that pressure just a little bit, lowered the pressure just a little bit, and it pushed me into a new regime that I wasn't wanting to operate in. I want to avoid that. So don't operate anything close to trouble spots. And critical temperature is one of the key trouble spots we pay attention to. We're also going to need to make sure that our column pressure drop is tolerable. Do you have enough energy in your feed stream that it can make it all the way through the tower, okay, without kind of getting bogged down due to our frictional losses? This is going to be really critical when you have a tower that's operating under vacuum conditions. You just don't have a lot of room to work with there. Also, the overhead vapor needs to at least be partially condensed at the column pressure so that you can have reflux happening inexpensively. Again, just like the reboiler, it's going to be an operational expense. If I have my condenser and my condenser requires cooling water, that's not a huge expense. It costs money, but it's not a huge expense. But if I have to add a refrigerant, now then I'm spending a lot more money. And so we would like to avoid that. The bottom's temperature for the tower pressure shouldn't be so high that I start ending up with chemical decomposition. Again, if you're expecting chemicals to come out and they decompose, that becomes an issue. And we want to avoid conditions where we have azeotropes forming. Now we're going to talk more about azeotropes in a following chapter. So how many different column separation sequences are possible? If I have a mixture of A and B, it's pretty clear that one column is going to make A and the next one will make B. And I just looked at one where I had A, B, and C, and I could say A will make the distillate, B and C will make the bottoms, and then I'll send these on to a second tower that'll make B and C. Or I can do A, B, and C so that I send A and B. C is my product here, and this one goes on to make A and B. And so I have two different ways to order this. But if I go to 4 towers, it's only 3 separations, so I've only added one more tower. But there are 5 different choices of ways to order this. And as I go up to more and more chemicals, I mean, look at this, 8. 8 doesn't sound like that many chemicals. 429 choices of orders for my separations. And our job is going to be to choose the best sequence for these separations. How on earth are you going to make a decision? And do you really have to analyze all 429 of these various possibilities? Surely we can shortcut this. So here's just looking at the 4-component problem. There are 5 options. These are the various ways that you can do this. And if you look at these, okay, that's interesting. How do you know which one is best? Well, as you're examining them first, again, remind yourself of those rules we looked at the beginning. If a chemical is thermally unstable, so if I heat it too much, okay, if it's corrosive, it's going to cause me to build my tower out of stainless steel instead of carbon steel. If it's chemically reactive, so that if it gets in contact with the wrong thing, it starts some sort of reaction sequence. Get rid of those fast, okay? Those guys are trouble. The other, after you've done kind of this is like a safety issue, so this is just an important thing to try and do. Then kind of remove your final products one by ones. You can just go as the distillate. That's a direct sequence. I mean, that's at least you don't have to think very hard. It's probably not your best choice, but it's the easiest logically, but not necessarily in terms of money. Okay. Look for sequence separation points that will remove the components that are the greatest molar percent in the feed. Again, we talked about this early, but if you remove the one that you've got a whole bunch of things, if you had one big component and lots of, little pieces of components, and you get rid of this one early on, then you can save yourself money, because now that I'm going to have just little dribs and drabs of things that I need to send into the distillation towers. That's going to be a much smaller tower. It's going to save me a lot of money, both on the initial purchase and in the operating costs for the heating and cooling of those towers. So to do something like this, it may be that in the order of volatility that they kind of went across this way. So I might have to do first a cut here and get rid of those guys, and then do a second tower and do a cut here and get rid of these guys, and then I have that purified. So it may not be the first tower, but work as a goal to get rid of the big elephant in the room kind of chemical. Look at those relative volatilities. So again, it's the relative volatilities that you're wanting to look at is the alpha for the two chemicals next to each other. Okay, and compare those and look for the ones that are easier. The larger that alpha is, that's going to be your easiest one. So the larger alpha is, the easier the separation will be. Okay. It says here, sequence separation points to leave last those separations that give the highest purity products. It's going to be very difficult to get a high purity product if you've got a whole bunch of other chemicals in there. It isn't too bad when you reach the point when you're down to a binary mixture to get to a very high purity. Unless, of course, you have something like an azeotrope forming. But so save these high purity final products as a final stage. And then sequence separation points that favor near equimolar amounts of distillate and bottoms in each column, as long as the reboiler duty is not excessive. So as we're doing this and we bring in our feed here, and I've got my distillate and I've got my bottoms product, if I need a whole bunch of distillate and just a little teeny amount of bottoms product, that's going to make for sort of awkward operation because I'm going to have a lot of material flowing in the top half of the tower and very little in the bottom half of the tower. Okay, so if you can keep those flows fairly similar in the top and the bottom half of the tower, it will make the design of the tower a little bit easier. So here's an example, and you might want to spend a little bit more time looking at these. So we've got the alpha values, and we see that all of these are greater than the 1.05. We said that was sort of a threshold for distillation is going to be problems. So all of these are easy. The easiest separation is this one, and this one is going to be my next easiest. So in order of ease, those two. The other two will be not bad, but, you know, similarly challenging. Okay? So we have these various chemicals, and I look at this, and so my easy separations are C3 and IC4, so that's an easy one, and C4 and IC5. Okay, so I have that one there. And then I look at my quantities. And if you look at these, if I separate just the propane, I get 45.4 and a whole bunch of other stuff. But if I separate here, I get things that are going to be kind of equimolar. So based on our heuristics, our rules of thumb, it looks like my first split probably should be here because it's an easy split and it keeps my quantities fairly evenly divided by the distillate and the bottoms. So I would do the first cut here, and then I would probably come in and look at maybe doing that separation next, and then continuing and looking at these. So let's just look and see what, you know, the solution was that the authors said that they would have considered, and they actually give several. This is not necessarily the best choice, but they looked at one and they said, well, let's just take off the C3 because that's an easy separation. So their choice of this one was because it was easy, okay? But you're going to have, like I say, 45 kilomoles per hour here. You're going to have like 840 or 50 kilomoles per hour here. So it's not a very even split. So this is questionable choice here. But next they did this one because this was the next easiest. Okay, and it kept a fairly even split. And at this point, you don't have any other choices to make. They just do these. So typically what we're going to do is we're going to choose, you know, 1, 2, maybe 3 options of sequence You know, I like to keep it to one or two if you can logically come up with a reason that these two are good choices. And we're going to complete the design on those far enough to get basic sizing and basic amounts of heat transfer. And then we'll very quickly look at economics and make the best choice of what these two are. So this concludes this lesson. In our next classes, we're going to start actually doing the design of multi-component distillation.